Hello, students. This is your friendly neighborhood chemistry professor, and we need to talk about titration. Now, what is titration? Well, the definition is a procedure for the quantitative analysis of a substance of unknown concentration, whereby a measured quantity of another substance of known concentration is completely reacted with the original substance, which sounds like blah, 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 blah. So let's take a look at the picture to the right. So what we usually see in the chemistry lab is a base in a burette. So this long, skinny, tall thing right here is called a burette. And we usually fill it up with a base of known concentration. So usually that's what we see first. So I'm going to scribble out acid, but keep in mind that in a different type of titration, you could have acid up there. But right now, the one that we're going to do has a base there. And the base is the one with a known concentration. So you'll have a bottle of base and it'll have a concentration on it like 1.5 molar KOH or 0.199 molar sodium hydroxide, something like that. You will know the concentration. And so you have the burette there, and it's on the burette stand, and it's got a burette clamp there, and it has this little valve right here that opens and closes. And the little plastic piece that goes in there is called the stopcock. And when the stopcock is parallel to the burette, that means you've got flow through the burette into the Erlenmeyer flask. And when the stopcock is perpendicular, it's shutting off the flow of the base down into the Erlenmeyer flask down there. Okay, so we got a flask down here, and you're going to have acid down here. And the acid is going to be of unknown concentration. Okay, so that's the typical setup in an introductory chemistry lab. And what we're doing is we're reacting the base with the acid and neutralizing it, and we're looking for calculation of the concentration of the acid using the volume of base that we used to do neutralization and the concentration of that base. And it's a lot of calculations, and we'll get there in a little bit, but that's the basic setup, okay? So acid of unknown concentration down here, base of known concentration up there. Again, we can reverse that, but in the introductory class, that's what we usually start with. Okay, so what does this look like on a molecular level? Well, here we have the Erlenmeyer flasks at the bottom down here, and they are filled with acid. And remember, we use H plus and H3O plus interchangeably, remembering that H plus doesn't really exist in water. It hops on a water to make hydronium, the H3O plus. And then you have a base up here in your burette. Now, it doesn't matter if you have sodium hydroxide or potassium hydroxide or one of the other bases that has hydroxide in it. What we're interested in is the hydroxide part of it, because the hydroxide is going to react with the H plus to make water, which is the reaction right here, okay? So when the stopcock, which is this thing right here, is perpendicular to the burette, there's no flow. If we turn it so that it is parallel to the burette, there's going to be flow, and you see that right there. And right there, that is a hydroxide ion, okay? And it's coming on down into the solution down there, and the hydroxide ion is going to find this guy right there, which is an H plus, and they're going to get together and they're going to make that molecule right there, which is a what? which is H2O. So that is right there. So you're getting a neutralization reaction. And how we are going to figure out when we are done is we're going to put something called an indicator in there. And the indicator is going to help us find the equivalence point where the concentration of H plus is equal to the concentration of OH minus. And the typical indicator used in introductory chemistry is phenolphthalein. Now, how we spell that and what that looks like, that's on a whole different slide. But phenolphthalein turns from clear and colorless to pink when it detects some base. Alrighty. So what does this look like graphically? Well, if we are in the Erlenmeyer flask, so down here, we're talking about the pH in the Erlenmeyer flask. So maybe we have a little probe here and it has a little wire that goes to a pH meter and it gives us X pH. And just imagine there's a burette up here. Ooh, my drawing is terrible. Sorry about that. But all right, so we're reading the pH on the acid solution. So it's way down here. And remember, acidic solutions have low pHs. And then we're going to start to drip some base in there. And as we drip base in there, the pH will start to rise. So if we look over here at this table, what we can see is that when we have not added any base yet, so volume of base added, the pH is down there at 1, which is right there. And as we add base, so you're adding milliliters of base there, you can see that your pH is increasing. And remember, acidic pHs are low and basic pHs are high. So this region right here, the hydroxide is finding the H pluses and they're neutralizing, and the pH is rising slowly. But once you get to this curve right here, your hydroxides are really having trouble finding H pluses to react with, and then all of a sudden they eat them all up and there's no more, and the pH goes, wah! That should be curving like that. There we go. And right here, where we have a pH of 7, that's where we have the concentration of hydronium equaling the concentration of hydroxide. And then if we get excess hydroxide, we're going to get this zone up here where it's basic. Okay, so at the bottom it tells us that the equivalence point is the point in a titration at which one reactant has been exactly consumed by the addition of a different reaction or the other reactant. So their concentrations are equal. Now for a strong acid-base titration, this is going to occur at a pH of 7. With different types of titrations, your equivalence point is going to be different. But right now we're just looking at an acid-base titration, a strong acid, strong base titration. So the equivalence point is at a pH of 7. All right, I promised to talk about phenolphthalein, but that means that I have to talk about indicators in general. So indicators, these are chemicals that are going to change color when the pH changes. So acid-base indicators, we usually add them to solutions in a very small amount, and it determines the solution's pH visibly. It changes color, so we can see where it's changing color. And these are usually organic compounds, and they're usually weak acids and bases. And if we look at the picture below, we can see that we have H end right here, which is indicating that this is an acid. Now, this is a weak acid, so it is in equilibrium with its conjugate base over here. So this is the conjugate base of H end. So see how H end, it loses its H plus and then it becomes end minus. So it's just like any other acid. conjugate base pair. And of course, the water and the hydronium are the base and the conjugate acid. But we don't put very much of that in there, and so it's not going to affect our reaction. So what you guys can see on the graph here is that when we have the protonated, or when we have the indicator with the H plus on it, the acid version, we're over here in the blue. But once we get to a position where most of the molecules are in the conjugate base version, over here in this side, we get the color that is yellow, all right? So if you put more acid into the solution, you're gonna have a lot of H pluses sitting around, and that's gonna give you a low pH, and the low pH is gonna show a blue solution. And once we go over into a basic zone, which is over here, that's when we don't have a lot of H pluses sitting around, and we have a lot of IND minuses sitting around, and that's going to be yellow for us with this particular indicator on this graph right here. Okay, so phenolphthalein, what does phenolphthalein do? Well, phenolphthalein turns pink at a pH between 8 and 9. So you can see that it's clear and colorless down here in the acid zone. And then when we get a little bit basic up in here, it's a light shade of pink. And then the more basic you get, the more pink it gets. So you guys can see right there how phenolphthalein works. Now, different indicators are going to change different colors, and they're going to change their color at different pHs. So it's important to find out what the best indicator is for your specific reaction. Now, that's not something that you'll have to do in this class, but just keep in mind that there are different indicators that work best at different pHs, and we get different colors. Now, what different colors am I talking about? Well, here's a really fun one, bromocreosol green. And this one goes yellow, green, and blue depending on which pH you have. So it is yellow with a pH below 4. And it's blue with a pH above about 5, a little bit above 5, like 5.4. And it's green in between. So that's kind of a fun one if we're going to be changing our pH from something below 4 to something above 5, we can see the change in the color. Another fun one is methyl red. This one has a change in color of pink to like kind of an orangey color around 5 and 6, and then a yellow color in the basic region. And if you want to see a chart of a bunch of different indicators, here's one. So we have methyl orange right here. Oh, we did methyl red, not methyl orange. Excuse me, let's take that off. We definitely did bromocreosol green, which is right there. And the phenolphthalein is right there, and methyl red is right there. So you can see, and this is pH on the top, you can see the pH zones where they're going to turn color and what colors they're going to turn. So bromocreosol purple, I like that one. It goes yellow to purple. I like yellow and purple, so that one's kind of fun. All right, so let's do some titration problems. So you've got 25 milliliters of a hydrochloric acid solution of unknown concentration. So where is that going to go? Is that going to go up here in your burette, or is that going to go down there in your Erlenmeyer flask? That 25 milliliters of hydrochloric acid that's unknown concentration. That's going to go down here. So you have hydrochloric acid in a solution, and that's unknown concentration. And then it says you titrate your acid with 17.3 milliliters of a 0.877 molar sodium hydroxide solution. Okay, so we've got sodium hydroxide up here in the burette. So this is our sodium hydroxide solution, and we know what the concentration of it is. So not only do we know that that's sodium hydroxide, but we know that it is 0.877 molar sodium hydroxide. Now, what is this 17.3 milliliter thing? Well, when you're reading the burette, you're going to fill it up with base, and then you're going to read the meniscus at wherever the base starts at. And wherever the base starts at, that is going to be your initial volume. So what if we started at 2.0 milliliters and then we titrated, so we opened the stopcock so it was parallel to the burette, and we dripped base in there until our phenolphthalein indicator told us that we had an equivalence point, and we got down to our final volume down here. So that would mean that, come on eraser, that would mean that we drained it down to there, and maybe that read 19.3. And we've got base in there right there. Okay, so if we had initial volume of 2, we read the bottom of the meniscus for that, and a final volume of 19.3, then our total volume of sodium hydroxide that we drained would be 19.3 minus 2.0, and of course that's milliliters and milliliters, and that's going to give us what? 17.3 milliliters. Okay, so that's where that number came from right there. Now, how do we do the calculation on this now that we know where everything is in the picture in the titration apparatus? Well, there's certain steps that you have to take, and they usually go in order. And the first one that you're going to want to do is you're going to want to write out the balanced equation. So what we have is we have hydrochloric acid, and we're reacting it with sodium hydroxide. So we'll go ahead and write hydrochloric acid and sodium hydroxide. That's an acid plus a base, so you guys should know that it's going to form a salt and what? And water. Okay. So 1 sodium on each side, 1 chlorine on each side, and we've got 2 hydrogens and 1 oxygen, so it's all balanced. This is an easy one, 1, 1, 1, 1, okay? And we definitely need the correct equation, and we need the balanced equation, because if we don't get that right, it's going to mess up all of our calculations. Now, the second part of this is you're going to use your volume and your molarity of your substance of known concentration. And you're going to calculate the number of moles of your unknown substance using the volume and the molarity of your known substance. Okay, so we use 17.3 and 0.877, and what we're going to do is we're going to start with the volume. So we have 17.3 milliliters, and this is NaOH solution. And whenever we are in milliliters, we usually want to switch to liters. So I'm just going to go ahead and put the conversion there for you. And that's something you should know by now because we're almost at the end of the semester. So we definitely should know that there's 1,000 milliliters in a liter and how to do that conversion factor. So there it is. So we canceled out the milliliters of NaOH. Now we're in liters. And we want to get from liters of NaOH to moles of HCl. So this is really interesting. But if you think about it this way, you're switching from one substance to another substance. And whenever we're switching from one substance to another substance, we're going to use what kind of conversion factor? A mole-to-mole ratio, because that's how we get from one substance to another substance. So first, we need to get to moles of sodium hydroxide. We're in liters of sodium hydroxide right now. And do we have something that relates moles to liters? We absolutely do. Molarity is moles divided by liters. So what we can do is we can go, okay, let's take that big M and let's split it up into its two little parts and put that 1 liter on the bottom and put the moles of sodium hydroxide on the top. And what number goes right here? 0.877. So we have 0.877 moles of sodium hydroxide per every 1 liter. And that's what 0.877 big M NaOH means. All right, now we are in moles of sodium hydroxide. And when we are in moles of something, we can go to moles of something else. So let's go ahead and put what we want to get rid of on the bottom here. And we want to put what we want to go to on the top. Okay, so we're relating moles of sodium hydroxide to moles of hydrochloric acid, or moles of HCl to moles of NaOH. And where do I get the numbers that go next to mole and mole? Right off the balanced equation. For every 1 HCl, you need 1 NaOH. Or for every 1 NaOH, you need 1 HCl. So we go ahead and cancel out moles of sodium hydroxide, and now we are in moles of HCl, which is good because we need moles of HCl to get to molarity. Okay, so whiz bam bang, we do the calculation with our calculator, and we go, aha, we had 3 sig figs right there. So what we're going to get, if I did my calculations correctly, is 0.0152 moles of HCl. Now, you guys, if I ever make a calculation error, which occasionally happens, please email me and let me know so I can make a new video and do the calculation correctly and not embarrass myself to the rest of the internet. Okay, so are we done? No, we're not done. We only have moles of HCl, and it asks for the concentration of the acid. Now, in order to get to molarity, which is the concentration, we need moles divided by liters. But we don't have liters of our acid. We have milliliters of our acid. Okay, so we need to change milliliters into liters. So, step 3, convert milliliters to liters. So we have 25.0 milliliters of our HCl. You can write that in if you need to. And again, we need to get rid of milliliters and go to liters. And this ends up being 0.0250 liters. So we have to put that together with that right there, and then we will be done. Okay, so now we calculate concentration of our acid, which is the stuff that's down there. And what we do is we put the number of moles on top, and we put the liters on the bottom. So now we have moles per liter, which is what? Molarity. And when we put this into the calculator, we get that we have 0.608 big M, HCl. And remember, the big M is moles over liter. So you could write moles over liter, or moles HCl over liter, or moles HCl over 1 liter, okay? But this is our final answer with the correct number of significant digits. Okay, let's practice that again because that was a lot. All right, again, we have 25 milliliters of an acid that we don't know the concentration of. So we've got acid down there in our Erlenmeyer flask. We're going to titrate this with 32.1 milliliters of a 1.50 molar KOH solution. So we've got the base up here, and we're going to drip it down into here until we reach an endpoint. And we're going to use that in order to get to calculate the concentration of our hydrobromic acid solution. So we need to write out the balanced equation first. So hydrobromic acid is HBr. And we're going to react HBr with KOH. And we've got an acid and a base, and so we're going to get a salt and what? And water, okay? So the salt is the potassium ion with the bromide ion, so cation and anion, and then we're going to have water. You can write H2O or HOH, whichever allows you to balance the equation better. Okay, so when we balance it, we're going to see that this is another one of those easy ones where we've got 1, 1, 1, 1. Make sure you watch out for the ones that are not 1, 1, 1, 1, and you'll occasionally encounter them, so be paying attention. Now we're going to use the volume and the molarity of the base to calculate the moles of the acid in the flask. So that's number 2 on the previous slide in our steps. And what we do is we start with the volume of the base. You start with the volume that goes with the concentration. There's no concentration that goes with 25 milliliters. The concentration here goes with 32.1 milliliters. And when we're in milliliters, we want to go where? 2 liters. Letting our units guide us, we're canceling out the milliliters. And now we are in liters and we want to get rid of it. So we put 1 liter on the bottom here. And molarity tells us that we can relate moles to liters. So we have mole KOH per liter. And what number goes next to mole of KOH right there? 1.5, and we got it from right here. So this is 1.50. So we've canceled out the liters now. And now we're in moles of KOH. And when we're in moles of something, can we go to moles of something else? Yes, and that conversion factor is called the what? The mole-to-mole ratio. So we're going to have moles on the bottom and moles on the top because it's a mole-to-mole ratio. And we want to get rid of moles of KOH, so we need to put it on the bottom here so it cancels out with the one on the top there. And we want to go where? To moles of HBr. Now where do we find the numbers that go here and here? Right off the balanced equation. So for every 1 mole of KOH, you need 1 mole of HBr to react. And again, it won't always be a 1-to-1 ratio, so watch out. Okay, so the moles of KOH cancel out, and what we get for moles of HBr, if I did the calculation correctly, is 0.0482. And again, that's moles of HBr. All right, am I done? No, you want molarity, not moles. And so we need to have another part, which is the volume. We need to divide the moles of HBr by the volume of HBr. And again, we said that right here we've got 25 milliliters, just like we did on the last slide. So 25 milliliters of a hydrobromic acid solution, and that needs to be changed into what? into liters. So 1 liter, and that again is going to give us 0.0250 liters. Okay, so we're going to put both of those together, and we're going to have 0.0482 moles of HBr divided by 0.0250 liters, and that will give us 1.93 moles of HBr over 1 liter, which is the same thing as saying 1.93 moles of HBr over liter, which is the same thing as saying 1.93 moles per liter HBr, which is the same thing as saying, oops, wait, hold on, I got an extra 1 in there. I was getting all crazy and it made me write the wrong thing. I bet you guys were like, wait, where did that extra 1 come from? Okay, which is 1.93 molar HBr, and this right here is what you will see on the bottle. Okay, and you'd pick up the bottle and you'd say this is a 1.93 molar HBr solution. All right, that is titration, and I will see you in the next lecture, which is probably buffers. Okay, bye-bye.